My differential capacitive touch pointer comprises just 4 paper-thin conductive pads and a small IC. The complete device can be fabricated as part of an ordinary circuit board. It works through thick plastic without cutouts. It could be placed under the cover of a steering wheel. Putting it in a keycap would enable a key to function both normally and as a high-resolution pointer. It can be operated through a sealed case, as in this handheld remote mouse. Measuring the position of a finger by its differential effect on opposing pads eliminates electrical noise and background capacitance, enabling error-free operation at high sensitivity. It has a 1,000-point resolution in each dimension, even through thick plastic. Theoretically, every pixel in a display could be mapped to a specific touch point, but no one can position their finger so precisely. Instead, it is used, like a mouse, as a displacement device. Sliding a finger over its face moves the cursor toward an object of intent in a display. At first, we want the cursor to move quickly, and we don't care about precision. As we get closer to the object, we want less speed and more precision. The device can help by increasing virtual movement at the expense of resolution, or vice versa. This is called acceleration, and all displacement devices have it. Acceleration is traditionally based on speed. Moving your finger faster moves the cursor further. 2 positions are needed to calculate speed, so acceleration lags. In a small device, the speed of a fast-moving finger may not be known until it is already leaving the pad. Shorter sample periods won't help because they are not reliable speed indicators. Other small devices briefly ignore speed changes and then suddenly accelerate too much. I developed a new approach using control theory. Acceleration is smooth and continuous, even while responding immediately to speed changes. You wouldn't know that the device is doing this, except that moving your finger slowly produces a small cursor displacement, while the same finger distance at a higher speed can move the cursor across the entire display. My device accurately interprets flicks and taps. This is not trivial. In a typical flick, the finger glances over the face, often without even one solid touch point. Larger capacitive devices like touch screens and pads discard this ambiguous hover information. This is not an option with a small device. I developed many different algorithms for interpreting this information. The best of these have only an 80% success rate, and when they are wrong, they can interpret a flick in the opposite direction. I couldn't improve these individually, so I developed a method for them to collaborate, essentially an algorithm of algorithms. Some that are not good on their own are very good at resolving conflicts between the better ones. This yields a nearly 100% success rate.